Welcome back to the joy of math and physics. Today I would like to demystify one of the most fundamental concepts in modern physics, namely the path integral, which is also called sometimes the Feynman path integral. This idea is of foremost importance, especially in quantum field theory calculations, which is the theory helping us push the frontiers of particle physics. The history of the story goes back to Paul Dirac, who envisioned the idea of the path integral, and to Richard Feynman, who developed it further. So, to motivate the idea of the path integral, let us start with a double-slit experiment of a particle like the electron. The experiment is composed of a wall with two slits, S1 and S2, and a detection screen in blue here. There is a source of the particles that could pass through either of the two slits and end up in the screen in a point which we call E. According to quantum mechanics, the particle could pass through slit 1 or slit 2 in equal probability. The probability amplitude is the sum of the two possibilities or paths. This idea is fundamental to quantum mechanics and is called the superposition principle. It allows the quantum particles to diffract and thus show also a wave behavior. So, if we want to find the probability amplitude for the particle to be detected in point E in the screen, then this is the sum of the amplitudes for the path to pass through the source O, then S1, then E, and plus the other path which goes from the source to S2 through the point E, the point of detection. So we sum the paths shown here with dotted white lines as you see and as you can see in the formula. So you can already sense that we are talking about paths. We will show shortly how we end up with the idea of the path integrals. So now we can make the setup more complicated. We could ask now what will happen if we keep adding another wall. For example, another wall with 3 holes in each slit, or with 3 holes in each wall. So we have another wall in orange here with 3 holes, which we call B1, B2, and B3. So now to find the probability amplitude for the particle to be detected in the screen at point E, for example, we need to consider all possible paths between the slits and that end up in the screen at point E, as you can see. So we have to consider all possible combinations of paths. And again, according to the superposition principle, the amplitude is then the sum of all paths that pass through the holes E's and BE's and end up in a point of detection E. So we have now to sum all paths that pass through the two kinds of slits, which I denote here with SI and BI. And you can see now that we end up with more paths between the 2 points. So we have the point of start, which is O we call here, where there's the source of the particles or the electrons, and we have the last point, which is E, and we want to calculate the probability that our particle will start in O and end up in E, considering all the walls and the slits. So we have to sum up a lot of paths, as you can see. But we can go, of course, further than this. And you can be more curious now and ask, what happens if we keep adding all the walls and more holes in each of the walls? So if we keep adding more walls, with each wall having increasing number of holes, we will then end up with having just empty space. So we can define empty space with just infinite number of walls between the start and the end, and with each wall having an infinite number of holes. This is a very trivial idea, but it's very helpful now for deriving the path integrals. Because now it tells us that the probability of the particle to start at point O and end up in point E would involve all the possible paths between the points, because this is the same as we having infinite number of holes in the way. So infinite number of holes means we would consider infinite number of paths. So in free space, for any quantum particle to propagate from one point to another, the probability that it will end up at that it will start and end up at these points would involve considering all the possible paths between the top points according to the superposition principle of quantum mechanics. And this is the whole idea of the path integral. If you want to find the probability amplitude of a particle moving between 2 points, then we would need up to sum all the possible paths between these points, even in free space. And this is a very radical idea because there is nothing like that in classical physics. In classical physics, if a particle wants to propagate from one point to another, then it would follow the path of the extremal action. So we do not need to sum up a lot of paths to find the probability of a particle to go from one to another. But in quantum physics, and because of the superposition principle, we would need practically to consider all these possible paths that the electron can take. So somehow the electron, in a very weird way, even in empty space, can take up all these possible paths with different weights to add up the probability that it will end up in another point. So this is the whole idea of the path integral. Okay, and all this is nice, but now how can we express all of this using mathematics and using the laws of quantum mechanics? If we want to sum up all these different paths between 2 points, which are basically infinite number of them, we have to quantify an infinite sum of paths. So how do we express this mathematically? Is boiling down how can we write down the sum of all possible paths between 2 points, and when there is an infinite number of them, we know what's the usual trick in mathematics. We have to come up with the concept of the integral, because the integral help us really quantify an infinite sum. So we can use the concept of the integral where the sum over infinite number of paths will be converged to the concept of the integral, or actually it's a definition of the integral where we have an infinite number of things we sum upon. So the sum over paths that we talked upon earlier, for example, in the context of the double-slit experiment, would now be an integral over all paths. And this is the basic mathematical underpinning of the path integral. So we need up then to converge this sum in the continuum to the integral of over all possible paths. Okay, so it is an integral of infinite paths between 2 points, as we have seen earlier. And now, this is the whole idea. As you see, maybe I would like to visualize this better. So we have 2 points, as you can see now, O and E, and we need to consider all possible paths between O and E, or possible curves, if you like. So you have O to E, it could take up, for example, this path, or it can take up this path, or that path, or maybe a straight line, so we have infinite possibilities of paths, because even though we are fixed between 2 points, there's a continuum of curves that could occur, and therefore we have an infinite number of them. But how do we sum a path? We have to really know how we can use the integrals to define this. So from classical mechanics, we define such an integral, which is called the curve integral. And the idea is we have to discretize our paths into secant lines with ends lying in the curves, or in our curve, as you can see. Then we can define the limit when discretization gets infinitely small. This would be then how we define an integral that sums over a path. So let's write down this using quantum mechanics. And let us get concrete now and write down that mathematically. So in quantum mechanics, the probability amplitude for a particle to travel between 2 positions, let's call them Qi and Qf, which would denote here O and A, in a time t, so it would take the particle to travel from these 2 points a total time capital T. then according to quantum physics, we need then to sandwich between the two position states a unitary operator that translates over space. And this unitary operator is basically exponential function of I or minus I times the Hamiltonian times the total time the particle would need to travel. So it's a very basic idea in quantum mechanics. We need the unitary translation operator to find the probability of a particle to go from point qi to point qf in total time capital T. And now our task is to show that this probability amplitude, which is given by this expression, can be written as an infinite sum of all possible paths between the point qi and qf. And that's basically our plan that we imagine to define the path integral. So as I said, here we denote qi is the position of the particle at point O, and qf would be the position of the particle at point E, which is the point of detection, for example, in the earlier setup that we described. So our first approach would be to first let us slice the time in equal intervals. So we need to discretize the time or the time capital T into equal intervals. And thus we will have to, of course, discretize our path into n secant points. And if we discretize our path, then we would need to discretize our path into lines, as you can see, or secant lines. And this is a basic idea when we approximate curves, as we have shown, as we can see or we remember from classical physics when we define the curve integral. So this is basically our approach. We need to discretize our time, and thus we discretize our path. And in the end, we will take the limit when our discretization or our step or time step or the length of our secant lines goes to 0, and thus approaching the limit when we get the curve. And of course, we denote here the time step of each of these lines, so to be dt or delta t, which is equal to the total time over the number of the intervals. So this is our basic approach. And of course, now we want to write the amplitude considering that. So because now we have our amplitude, total amplitude will be the sum of all amplitudes of small delta t instead of capital T, we have to multiply the unity operator for a jump from each of one of these discretizations or of these points lying in our in the ends of our secant lines. So we need up to our basically unitary operator will be n times of a smaller unitary operator for a smaller time delta t. So we multiply this unitary operator in times, and this is because if we sum all these delta t, we will end up with this capital T, and because we can sum the exponent of exponential functions, we get the earlier expression we have seen. But we just sliced our unitary operator into smaller slice, and we multiplied them in times. Which means basically we have n copies of the unitary operator e to minus ih delta t. So now we can massage the expression further. And the rest is mathematical massaging, and you can see, and we use the usual identities of quantum mechanics in which the principle of superposition will get manifested, and also the wave-particle duality. And among such very important identities or definitions is the orthonormality of the position states, which in continuum means that the inner product between these states will give us the Dirac delta function. This is from linear algebra function analysis, the requirement of orthonormality. And in position space, we can also make of still in position space, we can make of a very important identity or a definition, which is the identity operator. And this is a usual trick that we use all the time in quantum physics to simplify expressions. where basically we say if we sum or integrate over all possible states or continuum of position states of the bra and kit, this operator, if we apply it to any quantum state, it will give us the same quantum state. So it will just do nothing to any state. So we can always insert it. It will still keep mathematical equalities. And this is the identity operator we know from quantum physics. And now if we insert, for example, the other identity of the identity operator inside our expression for the amplitude, we for the state n minus 1, so this identity operator can be used with any state, and let's say we use it with the state n minus 1, then we would get up an integral inside our amplitude of the n copies of the unitary operator as we've seen in the previous slide. And so we will have this expression. We have an integral over dq n minus 1, and we have now sandwiched the bra and kit of q n minus 1 as you've seen. And as we have said, this will do nothing to our states because it's a unitary operator, it's equal to 1. So we are absolutely allowed to do this. But you can see now where I am trying to hit out. Now we can also insert this identity operator for all other states from n minus 2 early down to q equal 1 or to q1. So we thus get n minus 1 integrals for all these identity operators. So our transition amplitude or the probability amplitude curl A would be just, we'll have a product of integrals going from j equal 1 to n minus 1, and we sandwich all the bra and kits for these states inside our expression. Because all these are identity operators and they do not really do anything, and we are absolutely allowed to do this. But we have now a product of integrals of space. But we can also use these identities or these massaging to simplify this expression further, as you can see now. But we also see now that we end up with the concept of summing over paths, because now we are integrating all our coordinates from j equal 1 to n minus 1, and we are basically summing over paths. But we have a very hard to understand expression of the product of all these unitary operators, or the bra and kit of the unitary operators. So this boils down to a spatial integrals of that form, or a product of spatial integrals, and unit amplitudes of the form. We have a unitary operator e2 minus I h delta t times a position point, or between two consequent position states, or two adjacent position states. So this is our basic unit of all of this complex integrand. It's just a smaller transition amplitude between our steps, or between our discretization, because these q states are just the point slicing or this position states in our discretization. So as you can see, for example, this yellow line would correspond the transition amplitude to jump over this yellow line would be qj to e minus h delta t qj minus 1 if the yellow line has endpoints qj and qj minus 1, or vice versa. So this is our idea. We are integrating over all coordinates, we are summing over all paths of all these unit amplitudes, which are basically the amplitudes for jumping from one discretization point to another. But this expression is hard to handle and to interpret, so let's just massage it mathematically further. And let's look at the unit transition between 2 points lying in the path to simplify it further. So we look at an example of a unit transition like qj e2 minus I h delta t qj minus 1, and let me remind you that h is a Hamiltonian and it's an operator, so I'll denote it here with a hat, as you can see. And for simplicity, let us look at the case when we have a free particle. So there is a no external potential. And the Hamiltonian is then just the kinetic energy operator, which is basically p hat squared over 2m, where p is the momentum operator. And the momentum operator fulfills the following. If we act with the momentum operator in a momentum state, we will get a real eigenvalue which physically says what is the momentum corresponding to this momentum state. So if we apply the momentum operator to some momentum state, we get p, which is a real eigenvalue describing the physical measurable momentum. Okay, so far so good, and now let's go further with the simplification. So our unit amplitude will thus, or the amplitude, this unit amplitude will now can be written as the following: qj and then e to minus I delta t. Now we insert, instead of the Hamiltonian, the kinetic energy of free particle, which is p hat squared over 2m. Okay, so now let's do the usual trick, which is we insert our momentum orthonormal state as the identity operator. So we insert here an integral over all of the bra and kit of some momentum state, which basically boils down to 1. So we are always allowed to sandwich this identity operator. And we get the following expression. If we insert this momentum or this identity operator for the momentum states, where we have now 2 over pi, some normalization constant, and then we will get the following expression, where we have now integral over momentum. So our unit transition amplitude will be an integral over momentum over 2 pi, where now we have inserted the bra and kit of the momentum states. But you can see now where we can further simplify this. Because now this exponential function of basically the momentum operator in the exponent can be written using a power series. And if this power series now acts on our momentum states, so this is a power series in terms of p squared. So each time we apply p squared to our momentum state p, we pick up an eigenvalue of p squared. And we have a power series of p hat squared, we get then automatically a power series of p squared, and we can rewrite this power series as the exponential function. So we end up then with, if we apply this exponential function of p hat squared, we will get an exponential function of the eigenvalues, or the real eigenvalues of momentum p squared. So we have the same expression, but now p is no longer doesn't have a hat, it's just a number. It's just this real eigenvalue squared. But now we got rid of the momentum operator in the exponent. So basically we do not have any unitary operator anymore, because we got these real eigenvalues. And now the amplitude will become basically the integral TB over 2 pi. We get the exponent, or the exponential function outside of the brackets, because it's no longer an operator, it's just some number we can always get out of these brackets or these inner products. Okay, so now we have pulled out the exponent, and we have remaining these inner products between kj and p states, and between p and kj. So it's basically the same inner product, but it's reversed. But what is the inner product between a position state and a momentum state? So let's remember the wave-particle duality. If we project our position state over momentum state, we know that particles in quantum mechanics behave as waves. Thus, this expression will be just a plane wave for a free particle. So this expression kjp, or the inner product between kj and p, it describes the probability amplitude of the particle to be at position qj and have a momentum p, and this will be a plane wave like the form e to the I p qj. And the other inner product, which is reversed, will be the same expression, but we have a minus sign in the exponent of the plane wave expression. So now if we write down these results, in total we get from the bra and kits or the Ioana products the exponential function or plane wave expression a to the I times qj minus 1, where we get minus qj minus 1 from the other end product, which is a minus, which has a minus sign. But you can see now, and sorry for the mistake, there should be no hat here, it should be just p squared. So we have now an integral over an exponential function dependent on p. And this integral is just the Gaussian integral we know from calculus. There are many ways how can we solve this integral. And sorry for the mistake here, there should be no kj before the exponential function. So it's just the integral over momentum of an exponential function of p squared and the other expression that involves p. And we can of course complete the square to convert this integral into a Gaussian normal form, and we know how to integrate the Gaussian. It's basically will be some constant, and now if we perform the momentum integral after completing the square, we get the following nice expression. Because we have now integrated out momentum, we will get square root of m, where m is mass, over 2 pi I delta t times e to the I m qj minus 1 squared over 2 delta t. So this is basically it. This is the evaluation of the unit transition amplitude between the two adjacent position states qj and qj minus 1. It's just some exponential function that's dependent, of course, on the position. So now we can ask what is the total amplitude, because the total amplitude is a product of integrals over space, and the integrands are a product of such transition amplitudes, small transition amplitudes, as we have now evaluated. So we can multiply all these transition amplitudes to get the total amplitude. So the total, so we have the unit amplitude. We can write it again down, as you can see here. And in total, we will have a product of over all such unit amplitudes. So we'll have e to the I delta t m over 2 q1 minus q0, and then the q2 minus q1, and then so on until qn minus 1 squared. But we, of course, because these are just numbers, so now we do not have any operators. We have just an integral of product of exponential functions. And exponential functions, when we multiply them, we can sum the exponents. We can write this all these exponents summed up in a nice form. So so the final amplitude would be something like that. We have a product of integral symbols, or integral symbols, and we have an exponential function where the exponent is a sum of qj plus 1 minus qj all and then over delta t squared. And you can remember now we have, this is only a discretization of the path. This is not the limit where where we get exactly the curve that we are integrating. But you can already sense that in the exponent we have this qj plus 1 minus qj over delta t. When we take the continuum limit or the integral limit, we would end up with just a normal time derivative of the position. So this is now only a discretization of our paths, and we need to take the continuum limit, where we have infinite number of time steps or secant lines, or when n goes to infinity, where n is the number of intervals that make up the discretization, and of course where delta t goes to 0. If we take this limit, then the expression, for example, qj minus 1 over delta t will go, of course, in the continuum limit to the derivative of q over t, which is basically, you can say, the velocity along the path. And this is all well known from calculus classes. The same thing for the sum. When we take now the sum where n goes to infinity and delta t goes to 0, this will converge to our nice integral that we all know. So we have this sum of qj plus 1 minus qj will end up over delta t will end up to be the integral over the time derivative of the position squared. And then if we add up now the mass, we will have the integral over the kinetic energy. Thus, our amplitude of the particle traveling from point qi to or from the point qi to point qf in a total time capital T will be equal to the limit when n gets to infinity of some factor, and then we have a product of integrals of space and an exponent function that is I times the integral over time of the kinetic energy, because it's a free particle, so we have in the exponent only the integral of the kinetic energy. So what we are doing, we are because we have a product of integrals, we are basically summing over all paths where our integrand is some phase, where the phase is I times the integral of the kinetic energy. And this is something really, really weird and something interesting. Thus, our amplitude of the particle traveling from qi to qf in total time capital T, where now we have in the exponent of the exponential function a nice integral over the kinetic energy of the particle. We can abbreviate the expression for the product of all these integral symbols and their factors. So we have this factor im over minus 2 pi delta t over n, capital N to 2, and then we have the product of all these integrals. We can all write them with the limit in some symbol that abbreviates all this. And I will call this symbol, which is the convention when we write down path integrals, as integral capital dq, as you can see now. So this is basically the path integral, where we integrate over all passable paths between 2 points. And now you have, as you can see, I have abbreviated all these factors and the product of all these integrals with one symbol, which is integral symbol and then capital dq, where integral symbol capital dq will denote all these expressions that I abbreviated now. And we have to remember, when we always see integral capital D, we mean a path integral as defined earlier. Okay, so far so good. And this is basically everything about the path integral. We could have also looked at the case when there's also a potential energy term. And in that case, the Hamiltonian would be just the kinetic energy plus the potential energy. And the derivation, I would guess, so the Hamiltonian in this case would be just h hat would be equal to p hat squared over 2m plus the potential. And the derivation would be exactly the same, because this potential will not act really on momentum states, just some function of position. We will end up with the same, we will get then the same form, as you can see now. So the derivation will stay almost the same. And the integral will be something like that. So it will be the path integral, where we have e to the I of the integral over time of the kinetic energy minus the potential energy. And you can now ask, why do we have a minus? Because if you remember the unitary operator, it will have always a minus sign. So if you do the derivation, it would almost always stay the same. But when we always consider the potential energy, we have pick up always a minus sign. So it will be the integral over the kinetic energy in the exponent, of course, minus the potential energy. And then we sum over all possible paths. But this kinetic energy minus the potential energy exactly is the definition of the Lagrangian. And the integral over time of the Lagrangian is equal to the physical action. So our path integral formalism is basically we sum over all possible paths between 2 points, where we have a phase is basically the e to the I times the action, which is something really interesting, because we are summing over paths of over this weird complex exponent of the exponential function. And this is all the idea about path integrals. Now, as a final word, I want to say that we can also show that we get the classical physics from the path integral by getting the classical paths from this formalism, and this is done by taking the quantum to classical limit to the quantum to classical world limit. So how do we do this in quantum mechanics? We usually do this by applying the limit when h bar. So h bar is always something that measures or when h bar is not 0, then we are always in quantum mechanics. But if this h bar constant goes to 0, then there is the commutator between all operators is 0 always, and we get a classical world. So we have to take of this path integral, we have to take the limit when h bar equals to 0, and then one can show that we will get the classical paths or the paths of classical physics, and then one can show that classical physics contains within it the classical world when we take the limit h bar goes to 0. But this I will not do or not show here, because this would need more time, and this would be a separate video where we can nicely show how classical physics emerges from quantum or the path integral formulation of quantum physics. So as a final word, I want to say that this tutorial was based specifically on the textbook Quantum Field Theory in a Nutshell by Anthony Z, which I recommend to everybody, because this book is really conversational, comes with the really thought-provoking chapters, and it's not just a dry normal quantum field theory textbook, but it's very unique in its presentation, and it's also goes into details. So I would really recommend this book, which I based most of the information in this PDF on. So I hope you found this video useful to understand the path integrals and demystify some concepts about them, and that you also found the math behind them interesting, and looking forward to see you in the next video.